little prototype board for my charger that I'm building. There's a lot of stuff to learn, like the size of the toroid here, to the size and the ferrite material. This is the right material finally, so as you can see I actually didn't need to put that many turns on it, so that means I can run a smaller toroid, which is cool. And this is just an input inductor. I'm running just a simple Arduino Nano here for just a PWM. As I turn this knob, you can see PWM there. So right now what I actually have for a load is this it's a 500 ohm when it's cold, because it's positive temperature coefficient. Positive or negative? Positive, I think. Anyways, it's a 500 ohm soldering iron, and then this is a rectifier stage on the output. Basically, it takes the energy from the cap the energy out of this toroid goes into this cap, and then it gets rectified through these diodes here and into the soldering iron. I'm just using this as a load. This well charger battery, I'm going to actually hook that up next before I go upstairs for dinner, but right now I'm running 2 IGBTs on the input after this inductor here, and what they do is they don't have the anti-paralleling diode. That's inherently, naturally a part, according to what I've learned recently, of a MOSFET. But IGBTs actually they have to add the anti-parallel diode, so that if you're going to use these in a phase leg of a 3-phase inverter, for instance, the opposite IGBT to the one you're turning off will actually conduct the current when you turn the opposing IGBT or MOSFET on, as long as they have those anti-paralleling diodes. I actually have these because they don't have the anti-paralleling diode. And what that enables me to do is these are running parallel, and my next version of this charger will let me actually run 2 of these in parallel on the positive sine wave and 2 of these in parallel on the negative sine wave, and that'll rectify all the current and chop it up and put it into whatever I'm trying to charge. So that'll be depending on my turns ratio of my inductor. So for instance, to hook this up to 220 or 240 volt AC, you would wind this accordingly so that the output could charge, say, a 0 battery, and that's where I'm going with this. Or you could wind this for the output to be 470 volts for my Nissan Leaf powertrain that I'm running in my CRX. I need to build some sort of charger for that, and that's actually why I'm working on this. So we can zoom out with the oscilloscope, and you can see here that right now what I'm doing is I have this is a step down transformer. It's measuring, oh yeah, it's 24 volt. Nonetheless, it's a 24 volt output, so it's a way of cheating to test this circuit at lower voltage. So basically, I'm going to turn this knob, you'll see some PWM happening there, and then I turn it up far enough, we'll start getting some light there. That means it's actually powering my soldering iron right now. So we'll turn it back down. Now I do have a little bit of overshoot, so it's something I have to tune that, but that's a tricky part of this circuit, is tuning the way it all resonates, because if you have this wound, which for instance this is actually wound to run, this is actually designed right now, or wound more or less, to run a 64 ohm load on the output, and this is 500 ohms, so it's going to have a different ring. And what I'm measuring is actually the gate and the drain, I guess it's actually called the collector, and the emitter of the IGBTs. So we'll zoom in here a bit so you can see it a little better, and you can see it's not a horrible signal, but I do have to clean it up a bit. But as I said, if I change this to a resistance that's lower, that signal there will clean up. So nonetheless, everything's going good so far, so hopefully I can make some more progress with this.